I'm Professor Zoe Shipton. I'm a Professor of Geological Engineering from the University of Strathclyde, and I'm Chair of the Science Advisory Group for the UK Geoenergy Observatories. I want to take you to a place that we're all fairly familiar with, our planet. And as David said, we have to do something urgently to change our energy systems. In order to be able to reach an acceptable level of climate change, we need to introduce renewable energy into our energy system, and that requires energy storage, which, as David said, can be heat, it could be hydrogen, it could be methane. And all of these new technologies, geothermal, energy storage, carbon capture and storage, have big uncertainties around the science. In order to be able to de-risk those technologies, we want to run experiments. And unlike chemists and physicists that get to sit in labs and create model systems where they can control everything, as a geologist, it's an experiment that's only run once. And okay, it's been going for 4.6 billion years, but we really are very rarely given the opportunity to do controlled experiments in a really well-characterized system in the way that physicists and chemists are able to do. And this is what UK GOS will enable us to do. We are going to characterize a volume of rock on the scale of about a cubic kilometre in Glasgow, and another, it's like smaller in Glasgow, the bigger one in Cheshire, to a really incredibly unusual degree. We are going to know about what's happened down these boreholes, 12 boreholes in Glasgow and around 50 in Cheshire. We're going to have really good data about what's going on down those boreholes. That will enable us to build a three-dimensional model of what's going on in the geology. We'll have sensors down those boreholes and tools that are run down the boreholes to capture the physical properties of the rocks, how strong they are, how stiff they are. We're going to have sensors down the boreholes that listen to the earth and the changes in the earth that happen when we have earthquakes. The sensors that's going to go into the borehole here just across the road is going to be able to hear earthquakes from across the other side of the planet. But it's also going to be able to hear much smaller earthquakes nearby that might occur as the seasons change, or as Celtic Park, if somebody scores. I've actually had a seismologist check that. He thinks it won't register an earthquake, but I want to make a bet with him because I think it will. All of these science questions, apart from being really exciting for scientists, are really important to de-risk those technologies. If we are going to meet the demands of the Paris Treaty in terms of decreasing our reliance on fossil fuels and increasing the ability of ourselves to power our homes, heat our homes, and run our economies on renewable energy, we've got to be able to make it possible for businesses to come in quickly and utilise these new resources. And that is one of the things that UK GOS is going to be able to do. So, big science questions need big pieces of kit. So the physicists have their CERN, we now have our UK GOS. And this is going to be a laboratory that runs for, the design life currently is for 15 years. It will be an incredibly well-characterized volume of rock. People who design sensors will be able to test their sensors somewhere where they know the answers already to validate those sensors. They'll be able to test new ways of interpreting data and integrating data, inverting data to get new kinds of interpretations out of the ground. And we'll be able to run experiments. We'll be able to change the subsurface. So inject small amounts of fluid in and see what that does to the rocks, or take small amounts of fluid out. And David gave you a few examples of energy storage, carbon capture and storage, and geothermal. So if we think about geothermal in Glasgow, we're looking at, here we're not sitting on a mine, but just a few hundred metres across the Clyde, we're sitting on old mines. In fact, I've met some of the guys who mined down in those mines. And those mines contain warm water. It's not hot like Iceland, it's not boiling water, but it's warm. It'll be about 10 or 15 degrees C. Now that's warm enough to be able to turn your fridge backwards. You strip the heat out of the water and you upgrade that heat the way that it's pretty much the same engineering as your fridge, and you produce cold water. If you can pump that cold water back into the mines and let it heat up from the surrounding rocks, then you can repeat that process. People have done that. There are trial sites where that's done. In fact, the tall ship on the Clyde, just next to the Transport Museum, is partly heated by water from the Clyde. The heat stripped out of the Clyde is used to partly heat that tall ship, which is amazing. The Clyde's way colder than the stuff in these mines. But there's lots of science questions. If we do that too fast, will we pull all of the heat out and run out of the resource and drill some very expensive boreholes and put some very expensive backward fridges on those boreholes that then don't become economical? So we need to understand the heat, the thermodynamics of how the heat moves through the rocks and how the water that carries that heat moves through the rocks. The water in those mines is not pure water. It contains chemicals that are stripped out of the rocks from the mines, and anybody who's ever been in a mining district knows that mine water can be pretty nasty stuff. What happens when that starts to move about, and what happens when it starts to be heated up or cooled down? Things will happen, and we want to understand what they are. Really interestingly, there are microbes, there are bacteria that live in rocks down to a few kilometres deep. And this is a really cutting-edge area of science, understanding what happens to those bacteria. They spend almost all of their lives asleep until something changes that enables them to wake up and start metabolizing. And there are bacteria that eat methane, there are bacteria that eat sulfur and produce methane. Those bacteria will be present in the mines. Some of them will be from the rocks, some of them will be from the miners, maybe. Probably not. A microbiologist on the Science Advisory Group tells me that human bacteria don't live very well in rocks. But what will happen to those bacteria as things change in the mine? Sometimes they'll do things very helpful. Sometimes they might produce methane, which is something we don't want to happen. So all of these are science questions that we need to answer to be able to de-risk these future technologies. And without UK GEOS, we'll answer those science questions eventually. But UK GEOS gives us a platform to put a lot of science in one place, to piggyback on the findings of early studies to develop later studies, to really advance these technologies much faster than we otherwise would be able to. So the UK GEOS programme has been developed very much in collaboration with the UK academic community, and we've held workshops. This is a workshop at the Royal Society that we ran in the summer, where we've asked the scientists, what are the really big, exciting research questions in your field? We've asked the applied scientists, what are the innovations that need to happen to de-risk these technologies? And together, the Science Advisory Group pulled together what's called the science plan. That's kind of the ultimate what we wish to do, what we really would like to be able to do to understand these future uses of the subsurface. Now, we can't answer all of those science questions at one site, but we can answer an awful lot of them. And there's been a huge amount of work behind the scenes within the BGS to try and find sites and design facilities at those sites to answer as much of those science questions as possible. And this is a long-term project. Both of the sites, the Glasgow site and the Cheshire site, have a design life of 15 years. There'll be scientists coming here over that period to take samples, to run experiments, and we've gained real international interest. In fact, Susan Havorka from Texas came over to one of our workshops, and she left that workshop saying, I want one of these. I'm going to go back to the US Department of Energy and ask if we can have one. She was so excited about this idea of a long-term geological lab. This is a really exciting day for many of us in the room who've been involved in this project for years, building up the ideas. I think it's a really exciting day for Glasgow. I think having this in the Clyde Gateway is a brilliant thing for many reasons. Glasgow is actually developing district heat in a number of sites, which will be the end user for the heat that we might pull out of these rocks. I think it's really exciting as a place where children can come, future scientists and engineers can come and actually meet real scientists and engineers working and doing exciting stuff and pushing forward the sort of future of our energy system. So I'm going to leave it there.